As you have already seen on the invitation, this event is a little bit different than normally, where we only have one long talk. Today we have actually two speakers, Dr. Julia Venturini and Dr. Lorena Moreira, and they will both give a talk on their current research at ISSI. So both of them are postdocs at ISSI, and this is a special extra event that we created a bit because of two reasons. First, as you of course all know, last year we had much less possibilities to meet, much less than usually. Therefore, we thought that we will organize an extra event to compensate a bit for that. Of course, this is not a full compensation because the in-person interaction with the speakers is missing, and also the famous apéro is of course also missing, but I think it's still better than nothing. And second, we also hope that to establish a certain tradition here, because we thought that we also want to show the members of Pro-ISSI what research is actually going on at ISSI. And for that, we thought it would be a very good platform also for the postdocs to give presentations or then on their current research. So today we will do it like that. So we will start first with Julia Venturini, who will speak for maybe half an hour or so. Then it will be possible to ask questions. And then Lorena Moreira will give her talk. And again, afterwards, it will be possible to ask questions. As previously, you can either put your question into the chat, or you can also raise hand, use raise hand function in Zoom, and then we will unmute you and you can speak. Okay, so let's start with the talk of Julia Venturini. So before she starts, thank you very much, Julia, for agreeing to give this talk. This is really great. Thank you very much. So the title of her talk is Super Earth, Mini-Neptunes and the Radius Valley. And in case you don't know what the Radius Valley is, this is not some valley in the Swiss Alps or something like that, but this is a valley that has been observed in the extrasolar planet population. Yeah, you see the radius value of exoplanets. And this is a very interesting discovery, and it has triggered a lot of theoretical research. And Julia will speak about a new theory, how to explain this valley. But let me also give you some a very short summary of her CV. So Julia obtained her diploma in physics with the option astronomy at the Universidad de la República in Uruguay. So she's from Uruguay. I think it's also called the Switzerland of South America. Is that right, Julia? Okay, that is very nice. Then in 2016, she got the PhD in physics at the University of Bern, in the group of Willy Benz that some of you certainly know. Then she moved as a postdoctoral fellow to the University of Zurich, where she worked in the group of Ravid Hellet. And now since 2018, she's a postdoctoral fellow here at ISSI. Please, Julia, you have the floor.
Thank you very much, Christoph, for this nice presentation. And of course, thanks to the Pro-ISSI Association for the invitation, and to all the audience who are here connected to hear about exoplanets. So exoplanets are planets orbiting other stars than the Sun. And let's start by looking at where we are and where exoplanets are in our galaxy. So this is an artistic representation of the Milky Way. And here is where our Sun and us are in this arrow. And our galaxy, the Milky Way, has a diameter of approximately 100,000 light years. The Sun is at a distance of approximately 27,000 light years to the galactic center. And here in this circle, which has a size of between 100 and 1,000 light years, is where not only the solar system is, but also where most of the exoplanets that have been discovered until now are. And this might look very small compared to the size of the galaxy, but still in this little region, we have managed to discover more than 4,300 exoplanets. To be more precise, the amount of exoplanets as of today, it's 4,383. And The main lessons that we have learned in 26 years of discoveries of exoplanets is that they are very common and that they are extremely diverse. These two artistic impressions aim at illustrating such diversity in terms of orbital architectures, planetary masses, sizes, and compositions. But how do we infer such diversity? How are exoplanets discovered and characterized? Unfortunately, most of the exoplanets are too faint to be directly observed. So basically what we do is we rely on indirect methods. That is, we have to infer the presence of the planet by seeing some effect on the central star. Let's take a look at the transit method, which is the method by which most of the exoplanets have been discovered. A transit is produced when a planet passes between the star and the observer. Because the planet blocks part of the light emitted by the star, as you can see here now in the movie. This causes a decrease in the stellar brightness that we can measure. So that decrease in stellar brightness is directly given by the ratio of the radius of the planet over the radius of the star to the square. This means that if we know the radius of the star, we can, just by doing this measurement, infer immediately what is the radius of the planet. Approximately 2/3 of all the discovered exoplanets have been discovered by Kepler, which was a space telescope performing exactly this kind of method, doing transit method. What has Kepler found? So as I just said, it could measure the radius of the exoplanets. And this is here an illustrative histogram of the sizes of the exoplanets discovered by Kepler. Here is the size of Earth, and here is the size of Neptune. And you see that most of the exoplanets discovered by Kepler actually have sizes in between Earth and Neptune. Even when correcting for observational biases, this trend persists. So the smallest exoplanets size between Earth and Neptune are the most common ones. And actually, these planets, this size range, we don't have in our solar system planets with that size. So one naturally wonders what are these planets made of and how they form. Naively, one can naively extrapolate from the solar system and think, okay, maybe these are simply larger versions of Earth or smaller versions of Neptune. But what do we mean by Earth-like or Neptune-like? In terms of bulk composition, the Earth is simply a ball of rocks made of 1/3 of its mass by iron and 2/3 of silicates. And one might think that the Earth is rich in water because we have large parts of the surface covered by oceans, but actually the amount of water on Earth is less than 0.1% of its total mass. So from an astrophysical point of view, the Earth is dry. What do we know about Neptune? What is to be Neptune-like? We know for Neptune much less, unfortunately, than for Earth because we have much less data. This is why we need new space missions that give us more data about these far planets. But we know the mass, we know the radius, constrain interior modeling, and therefore say something about the composition. That interior modeling tells us that between 10 and 25% of Neptune's mass is in the form of hydrogen and helium. And in addition, we think that Neptune is ice-rich, and that's why it's often called an ice giant. But we actually don't know the exact amount of ices that Neptune has. For that, as I said, we need more data. Nevertheless, the term ice giant is probably not very off, because we know that the atmosphere of Neptune is volatile-rich, and we also know that the planet is located very far from the sun and therefore very likely accreted a lot of ices during its formation. Okay, so the difference in composition between the Earth and Neptune that we just discussed is also reflected in the fact that these planets have very different mean densities because of that different composition. So we could think that by knowing the mean density of exoplanets, with good accuracy, we could actually have an idea of what they are made of. This is a mass radius diagram of low mass exoplanets, exoplanets that have masses below 20 Earth masses. Here for reference, you can see a Neptune and the Earth. And it's all planets that have a good determination in mass and radius that is never below 50%. So something that is already very eloquent in this plot is that if we look at exoplanets that have the same mass, here we can see a large spread in the radius of these exoplanets. And this is already telling us, suggesting us about the large diversity in composition that I mentioned earlier. But can we really know the composition by knowing mass and radius? Besides all the technical difficulties of actually obtaining these measurements for these small planets, there is an additional barrier in this problem, which is purely theoretical, and it's called the compositional degeneracy. So what is this compositional degeneracy? It can happen that two planets that have the same mass, like illustrated here, with different compositions actually yield the same radius. So we will have planets with the same mean density, but that actually have different compounds. In this case, a massive rocky core and an atmosphere of hydrogen and helium, compared to a smaller rocky core with an envelope of water. This can actually lead to the same mean density. To understand a bit better this degeneracy problem, I give you a more daily life example. So imagine that the pandemic is over and you go to a party and your friend bake a cake. You're very happy because you're very hungry. But your friend tells you, I have a little quiz for you. You can eat the cake, but this is the only thing that you see of the cake. So you don't see the inside, you just see the mold. So the only thing you're allowed to do is to watch the cake, so more or less have an idea of the volume, and also to lift it, so to have an idea of the weight. That is to know the mean density. And she tells you, you will eat when you know, tell me what the cake is made of. And you start lifting the cake and you suddenly realize, I have no way to tell. I have no way to tell if this is a chocolate cake or a lemon cake or another flavor cake, just based on the mass and the volume. I need some other extra information to lift this degeneracy. This is this degeneracy problem I said. And then your friend sees your desperation and she tells you, okay, just tell me at least what this cake cannot be made of. Just let's rule out things and then you can eat. and then, okay, you say, okay, this has to be really a cake, so it's not made of air because it's too heavy to be made just of air. And also it's too light to be made of pure iron. I will have trouble to lift it actually if it would be made of iron. So at least you could discard compositions and then you can have your cake. And this is exactly what we can do with exoplanets. We can at least, by knowing the mean density, we can discard some extreme cases. For example, a planet that will adhere in a pure water curve, you know that it cannot be made just of rocks because otherwise it will be a much smaller planet and it will fall here. So we can have some idea and discard some compositions, and also by doing some statistical methods, we can assign likelihoods of possible planetary interiors. But let's go back to the radius of these Mini-Neptunes and of these super-Earth Mini-Neptune range exoplanets, because we actually know a bit more about them. Since 2017, reanalysis of the Kepler data with improved stellar properties revealed that the occurrence of exoplanets with sizes between Earth and Neptune is not flat, but actually follows a bimodal size distribution. So we have a peak of exoplanets at a radius of approximately 1.3 F radii, and a second peak at approximately 2.4. And we have this famous radius valley, this depletion of exoplanets at a radius of approximately 1.7 Earth radii. This bimodality was later on confirmed by several studies, so it's a very observationally robust result. So now we count with this very prominent observational feature to confront our models with. This means that we can try to run our theoretical calculations of planet formation and evolution and see when they are able to reproduce this bimodality. This might be a different way to gain insights into what these planets are actually made of. So to do that, now we go into that theoretical path. So I mentioned planet formation and evolution. So I will very, very briefly explain some important concepts of planet formation in one slide. Planets are formed as a byproduct of star formation. So in star-forming regions, we can actually see newborn stars surrounded by disks. This is called protoplanetary disks. These disks are accreting material into a star, are evolving. In a few millions of years, they are actually gone. So we need, in that time scale, which for us is a short time scale, a million years, to form the planets from this material in the disk. This protoplanetary disk typically have 1% of their mass in forms of solids, and it's actually these solids that have to start to stick together to form a larger object, which eventually will become a planet. The scales that range there are enormous. The dust initially is micrometer in size, and then it grows to millimeter, centimeter pebbles. It has to go through a phase of kilometer planetesimals, and so on, and until we have something like a moon mass embryo that can actually start to weigh some gas, and that can continue growing. And if this core becomes critical, that is several Earth masses, maybe it can start to accrete fast a lot of gas in a runaway gas accretion process. Like that, one can end up with a gas giant like Jupiter. So this is the famous core accretion model. This is the main paradigm of planet formation. So we start from small things and we grow bigger objects, and we need to form these cores first and then to start to create some gas. Another very important concept is that of the ice lines. So the ice lines, especially the most famous one is the water ice line. The water ice line is the location in the protoplanetary disk where the temperature is 170 K. For distances beyond so farther from the water ice line, the temperature is low enough so that water can exist in solid form. And this actually enhances the surface density of solids by a factor of 2, typically of 2. So beyond the ice line also we have more solid material, and this will help typically to make core accretion proceed. But this concept of ice lines is very important because it really creates a compositional gradient in the disk, and depending where the planets are growing, they will have a different composition because of this. But one also naively would think, okay, things that end up far out accrete a lot of ices, and things that are very close then should be completely dry. But things are not so simple, because another important processes occurring during formation is that of planetary migration, which I illustrate here in this movie of Frederick Masset. So the protoplanets, when they are growing the disk, they interact gravitationally with it, they exchange angular momentum, and typically this angular momentum exchange leads to inwards migration. So actually things that started forming far and are accreted ices can end up very close to the central star. Okay, having said this, we know there's a concept of planet formation, and actually, when we observe stars that have some planets, where we detect one of these transits, these stars are very old. They are like the sun, some few giga years old. So between the end of formation and that we observe the exoplanets that we actually detect, the systems went through a large term evolution of giga years. And during that evolution, the planets, if they have some atmosphere, the atmosphere can be lost or can cool down and be more bound to the planet. And actually, there are two processes that are purely from this phase of evolution, when the planets are already formed, that manage to explain this bimodality of the Kepler-sized exoplanets that I mentioned before. One is called photoevaporation, and the other one is called core power and mass loss. So both of them share that the fact that so they assume a simple planetary model. It's a core, a solid core, like coming from formation with a hydrogen-helium atmosphere, and this atmosphere will be exposed to certain source of heat. In the case of photoevaporation, they take into account the radiation from the central star. These planets, as I said, exoplanets are typically very close to the star, so they are highly radiated. And in the case of core power mass loss, is the heat remaining from formation that is included in the model. That is heat in the atmosphere. So there is a competency between the heating and the cooling of the planet, which will make the atmosphere contract. And because of that competition, it can result that when the calculations are performed, it can be shown that there are two equilibrium points. So in one case, the atmosphere can be completely stripped. The atmosphere escapes. So like the heat predominates. it's a competition of these timescales. And if there are equilibrium point, it can happen that the actually atmosphere has enough time to contract cool, and therefore it will be more rotationally bound and more harder to remove. So this other equilibrium point is a core with typically a 1% mass of envelope of hydrogen helium. And these 2 points is what then constitutes the 2 peaks of the Kepler size distribution that we know from observations. These models say something else, because not only they manage to reproduce the observations, but they actually only manage to reproduce them with a certain core composition. So they even give a prediction of what is the predominantly core composition of these Kepler exoplanets. And they see that it's a rocky one, it's a rocky composition, what matches good the 2 peaks that are observed. It's more clear in this panel than this one, but here they are all the curves together actually. So both models predict that these cores are rocky. So they say these planets might have very little amount of water and therefore probably form within the ice line close to the star. But actually this is at odds with planet formation theory. I already gave you the basic concept. So here we can see a result of population synthesis run here by the University of Bern, by Christoph and other collaborators. And the blue planets here are water-rich planets. And you see, because of what I explained you before, beyond the iceland there is more material, so accretion tends to be more efficient. And also planets that exceed 1 Earth mass tend to migrate very fast inwards. And that's why these populations, these simulations show that one ends up with super Earth planets that are typically ice-rich. What is interesting of this is that this is a very robust result. It's not only for one type of planet formation model. Many different types of simulations have shown actually that these super Earth Mini-Neptunes end up with a lot of water. This is another case in this work of Raymond and collaborators. So we have a problem because evolution models are pointing out towards completely dry planets or mostly dry planets. And formation points out to the opposite, that these planets should have a lot of water. And because of that, since I knew about the radius valley, the existence of the radius valley, I was very interested in this problem, and I therefore worked together with collaborators from Argentina and also from here from Switzerland. We managed to have a planet formation model that was quite complete. And at that stage, I told them, let's try to tackle this problem because this is very interesting. I will just briefly, because I don't have a lot of time, but so the main planet formation and evolution, we did planet formation and evolution simulations combined. So after the formation, Christoph actually computed the evolution of these planets. The main model assumptions are the following. So we consider a protoplanetary disk that is irradiated by a central star and also is undergoing photoevaporation, and also is accreting viscously towards the star. We include a model of dust evolution. It includes coagulation, fragmentation, drift, and ice sublimation. This is I put it in bold because this is a novelty of these simulations actually, and this makes at the end the whole difference. In this protoplanetary disk with pebbles, we insert a moon mass embryo that will grow by accreting these pebbles. It will accrete dry pebbles if it's in the inner part of inside the water ice line, and icy pebbles if it starts forming beyond the water ice line. So the protoplanet eventually grows to something like Earth or super Earth. Also, it's accreting some gas from the protoplanetary disks, and it's also, as I mentioned, migration. It's undergoing migration and typically parks close to the inner edge of the disk. After the million-year phase of formation and the disk dissipation, then we compute the evolution, including photoevaporation in this case, not core power mass loss, just photoevaporation during 5 giga-years. And what we found is that, do you see? This is the result of running hundreds and hundreds of planet formation simulations, barring the initial conditions that we consider ranges coming from observations of protoplanetary disks. And what the color, this is a histogram of the resulting mass of the cores that we form. This is at the end of formation. The blue ones contain large amounts of ices, or these cores are 50%, typically 50% water, 50% rocks. They accreted all the material beyond the ice line, and then they migrated inwards. And the red ones are really dry planets. They started forming inside the ice line and therefore accreted no water. And what this calls attention of this result is that actually we find a bimodality in these core masses, these cores that are produced after the formation process. So why does this bimodality occur? Why do we have these two distinct populations of very big and icy cores and smaller rocky cores? And this has to do actually with what I already explained about the ice lines, how it has to do with how the properties of the pebbles of these big dust grains changes at the water ice line. So the pebbles that are icy are more sticky, and therefore they have larger sizes, and this makes all the accretion process much more efficient. So a planet growing beyond the ice line will grow faster than a planet growing within the ice line. The formalities, one has to define all this Stokes number, but I think it's not really not necessary. If you want to look at the details, you can, and you can also write me later. What I want you to remember is this concept that the ice is more sticky, and therefore a planet will grow faster beyond the ice line. And not only will grow, so this will allow the planet in principle to grow until a larger mass. So then there is another important concept, because there is a limiting mass for how much a core can grow by pebble accretion. This is given by this concept of pebble isolation mass. And all I want you to know is that the pebble isolation mass is larger when we move farther from the star. So when we are at large orbital distances, this pebble isolation mass is larger. So the planet not only can grow faster, but also can reach larger masses because of this pebble isolation mass being higher at large orbital distances. And at the end, is these two effects what make that icy things can grow to bigger masses. And interestingly, just from the formation, so we have the composition of these cores, of these planetary cores, and we have the mass. So with simple mass radius relation, one can actually compute what is the radius of these objects. And when we do that, we get this histogram of the right, and you see that and the dashed lines are where the peaks of the Kepler size distribution are reported. So you see that we find actually a very good match with observations. This is very encouraging. There are some caveats with this, because this is just for the cores of the planets. Remember, I said that the planets are also accreting gas and they have a certain atmosphere. So we also, since we are computing that, we are including that in the model. We also computed with the presence of the atmosphere, the cooling with the photoevaporation. And then the story changes, and it looks in principle not so good. We have a lot of planets that cannot get rid of so much gas. But actually, there are other processes several processes that we are not including that can remove gas, and one of them is collisions. So we did some simple estimates, including collisions, during at the end of the formation phase, when collisions are more likely to take place. And in that case, then we can recover again the fact that to have planets that are more core dominated, and therefore will have a size distribution that is more similar to the core one that I showed before, and we recover somehow this bimodality of the planets, of the super Earth Mini-Neptunes. So as a summary, then more than 4,300 exoplanets have been discovered, most of them in our solar neighborhood. The Kepler Space Telescope revealed that the most common type of exoplanets are those with sizes between Earth and Neptune, and that they follow a bimodal size distribution with a radius valley at 1.7 Earth radii. Models are starting to be able to reproduce this radius valley, so it's very good. We are starting to gain some understanding into what shapes this process. In particular, our formation and evolution simulations showed that due to the change of the pebbles properties at the water ice line, Perl accretion leads to two distinct core populations, icy and large versus rocky and small cores. And such bimodality from birth leaves a valley imprint on the size distribution of short period exoplanets. And this is just for you to remember that the second peak should have a lot of water because they accreted beyond the iceland. Thank you.
Thank you very, very much, Julia. This was really very interesting. I could have listened to it for much longer. Thank you very much for condensing it. This was not easy. So I'm pleased to open the floor for questions. I see that there are already questions coming. Yes, Areli Casterion, can you unmute yourself? Okay, now I don't hear you. Yes, now.
Okay, yes, perfect. Hi.
Hello.
Hi, Julia. Thank you very much for your talk. This is really interesting. I'm currently working on a model to model super Earths to Mini-Neptunes as well. And I wanted to ask about the timeline when you begin accreting onto these cores, because I know the ice line changes depending on the luminosity of the star, and the star might be much hotter at the beginning of the disk than it would be at the a few million years after formation. So I wanted to know how that's dealt with in your model.
We are in our formation model. In this model, we are not including the effects of the stellar evolution during the formation. But that is, of course, I mean, the luminosity of the star is taken into account for the evolution part to compute the photoevaporation.
Okay, of course. All right, thank you very much.
You're welcome.
I think there was a question from Michael Losowski.
Hey, can you hear me?
Yes.
Yeah.
Hello, Michael.
Hi. So first of all, nice talk. Second thing, I'm just wondering, in your simulation, you take into account what you're forming below the ice line and then migrating inwards, right?
It's all taken into account together. What happens is that the things that grow beyond the ice line, they really grow so fast that the formation timescale is shorter than the migration timescale. So when they migrate the most is when they already acquire the Pearl isolation mass. I can show you. I can show you some here. Yeah, here you can see this is like planets in the same disk, and the red ones are the dry ones again, and the blue ones that are accreted beyond the ice line. And initially the ice line is here, but you see that these planets, yeah, when they stop, the core growth stops, they are still beyond the ice line, and that's why they keep all this amount of ice.
Okay, just wondering if our observations are pretty limited to a very close region around the star, and the ice line mostly is much more far out. So can it be something with our observation that we maybe see two populations, but actually there are much more those peaks that we just don't see? So just wondering if in your simulation, if you take into account the migration, it's very fast. So maybe you kind of lose some planets that are just still below the line.
Actually, I mean, you don't lose them. They tend to stop migrating close to the disk inner edge. So this is actually why we claim that these are exoplanets that we observe, because if they will remain very far, we will not observe them because of observational biases, right? So I'm not sure if I understood your question.
Well, I'm just wondering if it can be what we see, maybe two peaks, but there are actually much more peaks that are just still not available for us to see.
You mean from other ice lines?
Yeah.
Could be. It's interesting. Yeah, maybe when including a more complete chemistry model for the disk, one would see also other compositions. Still, the water ice line is the most important one. So the big jump in surface density occurs at the water ice line and not so much at the others. So yeah, but it's an interesting question, something to investigate.
Yeah, okay, thanks.
There was a question from Tilman Spohn who wrote into the chat. I will read it. So, what properties of pebbles exactly change at the water ice line? Density, I assume, but others as well.
Yes, very good. Density, yes, of course, but it's also the fragmentation velocity of these particles, and that has to do with the disk turbulence and with the sizes of the pebbles. So the fragmentation velocity of the, and of course with the material properties, no. So the dusty pebbles, rocky pebbles are much more easy to break. They have a lower fragmentation velocity, and this is what keeps the size low. It's this fragmentation. And smaller pebbles are harder to accrete, and that's what then makes the difference between the icy and the rocky ones. And these properties actually can be determined. It's a very hard measurements, but there are labs doing experiments with vacuum and putting aggregates of dust and seeing how they collide and how they grow. And of course, there is some controversy in what is the exact threshold velocity, fragmentation velocity to use. But in principle, this is included in the models, these values that we obtain from this experiment.
Are there more questions, please? Yes, another from Araeli Castellon, please.
Hi, hello again. I wanted to ask, when forming these cores, do you take into account any differentiation or separation of, say, the iron or the silicates sinking lower down and the ice is remaining on top?
No. That's too detailed for planet formation simulations.
Okay.
As far as I know, no planet, at least global models of planet formation don't include that. And I think also that happens a bit later, after the dissipation, because the planets are still at the beginning are very hot. When the disk is gone, they are still very hot, and then when they start cooling, is that you can have this core formation, the separation of the iron from the silicate. Yeah.
Of course. Thank you.
At the end, it's full of experts. This.
So there is a question from Mario Folanga, and he's asking, can we measure the composition, like, for example, water, obviously?
We can measure the composition. It's what I explained with this cake example, that we have this problem of degeneracy. So with mass and radius, maybe I can go back in the slides. Only with mass and radius we cannot tell. Something that is made pure of water would also be compatible with having a rocky core and a hydrogen helium atmosphere, for example, which is a likely scenario for something that is forming, because these are very abundant compounds. Hopefully what we can do in the future with transmission spectroscopy, when we know we have some constraint at least on what is the composition of the atmospheres of these objects. At the moment, those measurements are very rare, are mainly for hot Jupiters and not for smaller planets. But in the coming years, we will have much more of these measurements with GWST and with Ariel also. And hopefully that is an extra constraint for the interior modeling. And then we can maybe say, okay, this planet must have that amount of water or above this amount of water. Above or below, depends. Yeah.
So Maurizio was maybe also thinking of...
But also, sorry, and in reality, a planet made of pure water from a formation point of view is, I would say, impossible because of these ice lines. So in the ice line, here that you can see, the silicates are condensed almost in all the disk, and beyond the ice line, you on top have the ices, but the material, the building blocks of the planets already have rock and ice, so it's impossible to end up only with water, I would say.
Yes, Maurizio, I guess he was also thinking maybe of the the atmospheric composition that you just mentioned, Julia. Yes, indeed. Are there more questions? If not, maybe I can ask a last one. At the very beginning of your talk, you mentioned that we have so little data on an Uranus-Neptune, right?
Mm.
You said that this could be helpful, maybe also in this context. Where do you think see the links between Uranus and Neptune and these close-in planets? How do you think that this would be very helpful to improve our understanding?
That's a very good question.
Yeah.
Well,
I don't know the answer. I don't know the answer myself. I'm just wondering.
Yeah. Well, for me, after these works that we have done, there is a more clear link with things that we believe more that these planets, at least the second peak, are water dominate, that they accrete a lot of ices. And we also think that this is how Neptune formed. So I see a connection from the formation point of view. Of course, the conditions are completely different. I mean, these planets that we are discovering because of the observational biases, we can only see them very close to the star, and they are very hot, and they are undergoing all this process of photoevaporation that never happened to Uranus and Neptune. But I think the link is more with the formation, because if we could know better what is the exact amount of water in relation to the rocks, this can give us further constraints for our formation models, perhaps.
Yes, yes. Maybe just the bulk composition, which we know very poorly in principle for the ice giants. Yes.
And also, I mean, it's a bit weird. We call all these planets sub-Neptunes, mini-Neptunes, and we don't actually know what Neptune is. It's a bit frustrating.
Yes. Yes, I mean, Julia Venturini was mentioning that also because there are now discussions of a future large mission to the ice giants. And there are several options, of course, and one would be to go to the ice giants. I see that the time is already well advanced. I would like to thank Julia again. Thank you very, very much.
Thank you.
I would like to move on to our second speaker of today, who is Lorena Moreira, as mentioned at the beginning. And her talk, we change really completely the subject, which is, I think, nice. Although we still talk about water, I may say, but maybe not the same amounts of water, but still, because the topic of her talk actually is the origin of the regional and interannual variability in the sea level. And before Lorena Moreira starts, let me also quickly go through her CV. So Lorena Moreira origins are in Galicia in Spain, a very nice region, I may add. I have been there. And she then graduated in physics at the University of Santiago de Compostela. And she also got a master in climate science, so the two things together, at the University of Vigo. She then obtained her PhD at the University of Bern as Julia, but from a different institute, because she obtained a PhD from the Institute of Applied Physics, where she was working with Professor Nicolas Kampfer and PD Dr. Clemens Höcke. And then in December 2019, she moved to the sea level topic and started the postdoc at ISSI under the supervision of Dr. Annie Sazanav. Yes, please, Lorena, you have the floor.
Thank you. Good evening, everyone, and thank you very much for the introduction and for inviting me to the Pro-ISSI talk series. Julia talked about the formation of planets, and I will talk about the destruction of our planet. So it's a funny thing. So I will start explaining why the sea level is rising, and then I will talk about regional and interannual variability in sea level. So as we all know, sea level is rising and its consequences are very dramatic, as we can see in these example photos. Most of the big coastal cities are already implementing mitigation plans to cope with the sea level rising problem. For example, the Indonesian government has planned to move its capital city from Jakarta to another city in Borneo Island. The sea level will not stop rising anytime soon. And this map shows the sea level projection performed by the Climate Central Organization for the city of Amsterdam, assuming that emissions will not be cut, which is the business as usual scenario. In this situation, in 2030, which is close, the airport will be below water level. This is just an example. They don't take into account the plans for this sea level rising problem, but you can go to their website and check the projections for any coastal city you would like to see. And the sea level is not only rising, but it's also accelerating. And this figure shows a global mean sea level measured by satellite altimeters since 1993, processed by Lagos in France. It is observed an increase of about 9 centimeters in sea level for the altimetry era. During the first decade of the altimetry era, the sea level increased by 2 centimeters. During the second decade, 3, and nowadays is going to be close to 5 centimeters. So since the beginning of the 90s, the sea level change can be monitored from the space using satellite altimeters. These satellite altimeters orbit the Earth, flying around the planet within 10 days and measuring the sea surface height with a precision of a few centimeters. Here I show the timeline of the constellation of high precision altimetry missions since the beginning of the 90s. When the first satellite altimeter, the TOPEX Poseidon, was launched in 1992, up to the most recent one, the Sentinel-6 Michael Freilich, launched in November last year, and also in yellow, some planned future missions. But how the satellite altimeters work? The radar altimeter on board the satellite bounces a signal of the ocean surface, and when the signal comes back to the satellite, it measures how long it takes to go down and come back up. And then we can deduce the distance between the satellite and the ocean surface, which is known as the range. But in order to estimate the sea surface height, we also need to know the position of the satellite in the space. Satellites have 3 different positioning systems that determine where the satellite is. From the orbit of the satellite, we can deduce the altitude of the satellite with respect to the ellipsoid. The ellipsoid is a rough approximation of the surface of the Earth. And with these 2 pieces of information, the range and the altitude of the satellite, we can get the sea surface height. And finally, we can average all the measurements over the whole oceanic domain, and then we obtain the global mean sea level curve that I showed you a couple of slides ago. So now we know sea level is rising, how we measure, but why is the sea level rising? To understand this, we first need to understand how our climate system works. The most important source of energy for our climate system comes from the sun. This energy goes through the atmosphere and warms the surface of the Earth. And then the Earth radiates energy back to the space. But since a few decades, the Earth is in a state of energy imbalance, which means that it emits less energy to the space than it receives from the sun. This also means that energy is accumulating heat is accumulated in the Earth climate system. But why is the Earth emitting less energy? The reason for the Earth energy imbalance is the change of the composition of the atmosphere that we humans are causing. As we emit greenhouse gases to the atmosphere, these gases absorb the energy that is supposed to be emitted. They trap the extra heat, and as a consequence, the Earth system warms up. And what happens with this extra heat? Over 90% of the heat that is trapped by these greenhouse gases is accumulated in the oceans, and because water has a much higher heat capacity than the atmosphere or other component of the climate system. And as one of the most dramatic consequences of this extra heat is the rising of the oceans. And this is known as a cause-effect mechanism. As we increase the concentration of carbon dioxide in the atmosphere, the amount of energy emitted by the Earth is reduced, and this extra heat warms up the Earth climate system, so the surface temperature of the Earth increases, and as a consequence, the sea level is rising. This figure shows the increase in carbon dioxide concentration since the 80s, measured by ice core and marine surface sites, is shown in orange. And then the temperature anomalies measured by satellites shown in the rainbow colors, and the sea level measurements from tide gauges and satellites showing in blue, showing an increase in sea level of about 15 centimeters since 1965. So the current sea level rising can be explained by two main causes. As the water warms up, it expands, and this is known as thermal expansion, and represents 1/3 of the modern day sea level rise. And the other cause is the input of fresh water in the oceans due to land ice melting, and also a small contribution due to changes in water storage on land. And together, those other things represent the other 2/3 of the modern day sea level rise. But to understand who causes the sea level rise, we use the concept of budget. So the observed global mean sea level rise can be explained by the sum of the steric component and the ocean mass component. The steric component refers to changes in temperature and salinity, and the ocean mass component refers to changes in the ocean mass or in the mass of the glaciers, ice sheets, and terrestrial water storage. To estimate the components of the sea level budget, we have different observing systems. As previously mentioned, we have the constellation of high precision satellite altimeters to measure sea level change. And to estimate the ocean warming or ocean thermal expansion and salinity effects, it is the Argo project. The Argo project started in year 2000. There are about 3,900 profiling floats that measure temperature and salinity down to 2 kilometers. And to estimate the change in the ocean mass or the change in the mass of the components of the sea level budget, we have the glaciers, ice sheets, land waters. We have GRACE. GRACE is a space gravity mission launched in 2002 that infers mass redistribution over the surface of the Earth. This figure shows the time series of global mean sea level in black, and the components of the budget in different colors from 1993 to 2016. The red line represents the sum of the contribution from thermal expansion, land waters, ice sheets, and glaciers. And the global mean sea level and the sum of the components agree well, and this indicates the closure of the budget, means that we can explain how sea level is rising. So, but we can also study the budget using data from GRACE mission. But this is for a shorter time span because GRACE was launched in April 2002. Is in the figure the blue line, and the orange line shows the thermal expansion measured by Argo floats in 2005 and processed by GPL. Again, we state the closure of the budget, but how much each component is contributing. In both pie charts, we see that about 30% of the contribution is coming from thermal expansion and about 60% from the ocean mass component. but also some contribution of an unknown signal. This slide shows the ice mass loss from Greenland and Antarctic ice sheets measured by GRACE. Between 2012 and 2020, Greenland has lost about 280 gigatons of ice per year, which are about 0.8 millimeters per year rise in global mean sea level. In case of Antarctic ice sheet, the loss of ice was about 150 gigatons of ice per year, and resulting in a global mean sea level rise of about 0.4 millimeters per year. This is a graphical example of how much ice the Rhone Glacier, which is located here in Switzerland, has lost in the recent years. The image on top was taken in summer 2009, and almost 11 years later, last summer, the glacier was as in the image in the bottom. And this figure in the left-hand side is from the Swiss Glacier Monitoring Network and shows that the glacier is more than 1.5 kilometers smaller than it was in 1879. And you can check in their website the status of any glacier in a Swiss glacier. And now I move to a next topic. This figure shows a map of the regional sea level trends over the whole altimetry era from 1993 to May last year. And the first thing we notice is that sea level is not rising uniformly. There are regions where sea level is rising about 3 times faster than the global mean. For example, the regions where the reddish color are like Southern Pacific Ocean. So we conclude that some spatial regional patterns are amplifying the global mean sea level rise. And this the map in the left-hand side shows the sea level trend from altimetry from 2005 to 2018, and the map in the right-hand side is the trend of ocean thermal expansion and salinity effects for the same time span. And we conclude that the regional sea level variability is mostly due to non-uniform changes in heat content. And the map on the bottom shows the trend of the sea level after removing temperature and salinity effects, which indicates that the regional sea level trends are still mostly driven by internal climate variability. So now I am going to talk about the presence of interannual variability in global mean sea level. Our initial goal was to estimate the evolution of the global mean sea level rate and its acceleration. However, global mean sea level is impacted by interannual natural variability that needs to be isolated and removed to properly estimate the rate and the acceleration. In other words, we need to identify which of these bumps are due to a natural source and which are due to an anthropogenic source. From recent literature, we know that the ENSO phenomenon plays a key role in the interannual variability of global mean sea level. The El Niño Southern Oscillation is one of the most important recurrent climate phenomena on Earth, due to its ability to change temperature and precipitation patterns across the globe. El Niño and La Niña are the extreme phases of ENSO. In the figure in the left-hand side are represented the trended global mean sea level in green, which is the interannual variability, and the ENSO signal in red. The correlation between these two curves for the period between 1993 to 2020 is about 55%. So we can explain some of the bumps and dimples in the interannual variability of global mean sea level due to ENSO. And the two maps on the right-hand side show the terrestrial water storage changes during ENSO events. These maps are from the ISSI trip hydrological model. When we have an El Niño event, we got a rainfall excess over the tropical Pacific, over here. and water storage deficit over tropical land. And then the global mean sea level temporarily increases, as we can see here, and as a consequence of this. No? And the opposite effect occurs during La Niña. During La Niña, we got excess of rainfall over continental areas in Australia and Indonesia, and more water storage over this tropical land. And the global mean sea level temporarily drops, as we can see here. So we certainly need to remove this interannual natural variability to properly estimate the rate and acceleration due to externally forced global climate change. Here I show you the dominant periodicities that are present in the observed global mean sea level using a long Scargel periodogram. The red line indicates that the peaks detected above the line are with a 95% confidence level, not due to random fluctuations. So the observed global mean sea level contains statistically significant peaks at 3 years, probably due to ENSO, at 6 years, and at 12 years, probably related to the Pacific decadal oscillation. And in this figure are represented the rolling trends, the rates over 5-year window shifted by 1 month of the corrected global mean sea level. What we did was we tried to remove the influence of the interannual variability using 2 different methods. However, some interannual variability is still present in the corrected global mean sea level, but has a smaller amplitude than in the original one. No? Still, this remaining signal impacts the estimation of the global mean sea level rate of rise, and of course, the estimation of the acceleration, of global mean sea level acceleration. And in this remaining interannual signal, we found an unexpected 6-year cycle that is also observed in some components of the climate system, as for example, the rotation of the Earth, the temperature of the surface of the Earth, and some components of the global mean sea level budget, and some climate indices. So to conclude, we can state that the current global mean sea level is rising and accelerating, and we can explain it due to human-induced land ice melting and ocean thermal expansion. However, more work is needed in order to improve the methodology to remove the interannual variability to properly estimate the global mean sea level acceleration due to externally forced global climate change, and to understand the origin of the 6-year cycle reported. At regional level, the spatial trend patterns are mostly due to non-uniform changes in ocean heat content and are still mostly driven by internal climate variability. So thank you very much for your attention. That's it.
Thank you very much, Lorena, for this talk. This was very interesting to see all the a little bit frightening developments, but of course that makes it even more important to investigate it and to understand, try to understand what causes it.
Yeah.
So please, are there questions? Yes, from RM Bonnet. Please unmute yourself.
I think I am unmuted.
We can hear you. We can hear you.
You can hear me. Very good.
Yes, perfect.
I just have a question which has never been answered to me. To what altitude in the atmosphere is the temperature being measured? And just to follow whether the modification in the climate also impacts on the atmosphere.
At which altitude the temperature in the atmosphere is?
Measured.
Measured.
Well, we can measure the temperature in the atmosphere from the troposphere up to the mesosphere, but the sample I show here is surface temperature, the temperature where we live.
but you can also measure it quite high up. This
Yes. This is from my past in the during the PhD that were.
Yes, I thought that this is exactly this topic. Yes.
It's constant. The temperature is constant.
No. It's a very clear profile. Decrease now, decreasing and then increasing again, as far as I remember. Is in the stratosphere opposite to ozone, so we can. Is the reason why we can live here in the Earth.
Thank you.
We can discuss this later.
Yes.
I can show you profiles of temperature.
Thank you.
Are there more questions, please? Yes, from Tilman. Please, Tilman. Do you want to speak up, please?
Yeah, thank you very much, Lorena, for this nice talk. I had a question about the correlation between the ENSO and the sea level change that you said was 55%. So I was wondering, isn't that a pretty, low coefficient, correlation coefficient? So I would have thought it would be more, actually.
Yeah, well, you can see by eye that the.
But in terms of cause and effect, I mean, is that, a little weak, actually, isn't it?
Yeah, but we are talking about the global mean sea level and one climate index that is measured in the tropical Pacific. So yeah, and the whole message here is that even though it's affecting mostly the Pacific, it affects the whole planet, but we see the effect, and you can think that it's small, but if you compare the two curves here, it's small, but it has an impact. And when we have an El Niño event, you see the increase in the global mean sea level, not only also in this curve, but also here in 1997, you see this bump here, and then we see in 2011 we had a La Niña event, and you see how the global mean sea level has decreased. So yes, it's a global effect from a phenomenon that occurs in the tropical Pacific, but yeah, it has impacts over the whole planet.
Okay, thank you.
Welcome.
There is another question in the chat that I would like to read. It's from Paul Temme. So thank you very much. In one of your pictures, I saw south of maybe a Greenland, I'm not sure, a decrease of sea level. Is the salinity change to sweet water inflow the reason for this? Yes, it must be Greenland, I guess.
Yeah, you probably mean, you probably mean this one, no? Yes, this is something that we are studying. We are trying to detect the fingerprints from present-day land ice melting from Greenland. In this case, you see this blue region here, southwestern Greenland. Yes, we can see the effect in salinity, but also we will correct from the ocean thermal expansion, but in the steric are both considered. The steric considers the thermal expansion and salinity effect. So yes, this signature is probably the ice sheet melting in Greenland.
We have a next question from Claudio Caccia. Thanks a lot for the presentation. Are there any clues to explain the 6-year periodicities you mentioned?
Yeah, well, we are working on that. Yes, yeah, we see this 6-year periodicity in some other components of the climate system, as I mentioned, the Earth's rotation, and in the surface temperature. And in the steric component and in some climate indices, but so far we are not able to say this is due to this, something that is work in progress.
There is a question from Maurizio.
Yes, first of all, thank you very much. It was a beautiful talk. I have a question about one of your first picture and even one of your last picture, where I guess nobody wants to see the airport of Schiphol in Netherlands underwater, and nobody wants to see disappearing Venice underwater. So we saw very beautiful that, well, unfortunately, it's increasing the sea level and even expanding. So in European, one of the first measurement.
Could you repeat, because it was some noise? Maybe write it in the chat.
Maurizio, we couldn't hear you for a second.
Oh, sorry. What should we do to stop the sea level rise, in your opinion, one of the first measurements?
Even if we do things now, will not stop rising, actually. Yeah, we should cut the emissions, actually. And now for coastal cities, move back or implement mitigation plans like putting some vegetation to stop the rising, and yeah, probably stop dirt in the earth. Yeah. But yeah, you see, it will not stop. I think, as the projection said, I don't know, but they say that will not stop. For example, this is the worst case scenario, but it's 2030. I don't think they will cut emissions before 2030. So this is why I selected this unchecked pollution scenario, but probably. But yeah, Amsterdam has plans to prevent this. They are constructing things to avoid you have to take a boat to take the plane. Well.
Thank you, Maurizio, for the question. There is a next question from Anushka. Thanks to both speakers, she writes, has the frequency of the ENSO events been observed to change? And the predictions and modeling of ENSO?
It is not my area of expertise. I have some ideas. I listened in the past. Yes, I think the answer is affected by anthropogenic sources, but I cannot reply because it's not my expertise.
No problem.
Sorry.
Oh, that's fine. Questions. I would have myself, maybe the last one in case there is no other one. You spoke about the salinity effect. So do I have to imagine that locally the salinity in the oceans is non-uniform and evolving in time, or what is exactly meant by that?
It's non-uniform. And what do you ask?
So this changes because, for example, fresh water is added and the salt content is locally smaller.
Yes.
Or is it also sometimes rising when you have strong evaporation locally in the equator, for example?
Difficult question for me. I'm not sure. I am aware of the ice sheet melts, you have fresh water input, and then the salinity actually will change, but then this water will be mixed and kilometers far away from the source of the melting. So yeah, as far as I remember, representing the salinity trend maps, it has a non-uniform patterns. Yes.
Mm-hmm.
Yes.
And if I remember correctly, then salinity gradients can also affect the thermal gradients, how the mixing inside of the oceans is affected by the salinity.
Yes.
So you could have a link between that.
Yes. Yes.
Okay. Let me quickly check if there is another question. Okay, if not, Lorena, Moreira, thank you very much. Also you for your talk. Thank you very much. It was very interesting, a lot of questions. I think I would, in this case, start to close but before we really stop, let me use the opportunity to inform about the next future Pro-ISSI events that we plan. So in October 21, we should have the talk by Wei-Qing Han from Colorado, and then in March 2022 by Sabine Schindler from Innsbruck in Austria. And both of them are Johannes Geiss fellows. And but this is still TBD. And of course, we hope at some point to be back to normal operation in persona meetings. At the moment, I think it looks good, but when exactly it will be possible, we don't know yet, right? But we will see, and we will, of course, keep you updated on that. But before we disconnect, let's thank again our two speakers of today. Thank you very much. Thank you very much.